the flow, let me say, of the sustainability. It will be just a flash introduction from my side to the next section that is more on the sustainability. Let me say, product point of view. You know, yesterday we have understood that the key point is actually to reduce the CO2 emission per square meter in the building. And we can say that our approach is to have two potential solutions, let me say. One solution is simply to, let me say, to build with the low carbon cement. So it's normal to reduce the CO2 emission per cubic meter and then for square meter by reducing the CO2 emission in the cement. And so in this way, we can say that the concept of 2AL cement that will be now presented by Soren is in this way. So we can have the same amount of concrete for a foundation, or for a slab, for let me say, an aesthetic wall, but using a cement with the low carbon. So potentially we'll have lower carbon cement and so lower carbon product. So this is what we are, let me say, we have listened to our customer to do. So switching from CEM1 to CEM2, add the slag or so on, or just to have a potential CO2 emission in the binder lesser than before, keeping the same material quantity. And then the other concept is to build more with the less material. So in this case, the concept is to reduce the material itself, to do higher strengths, like with the UHPC, instead of the traditional concrete, or instead of having, a wall with a thickness of 35 centimeters, we could have a wall with 10 centimeters, and this is very important because we save the mass of the material. So from the building point of view, precast point of view, is less CO2 emission per square meter in this case. So this is the key point. And then here there will be another presentation on this focus on this point is the innovative solution based on the UHPC. So it's a solution that is pointing on saving material with the better performances. Obviously, in our point of view, the first part, let me say, it's based on the customer, or it's based on us. So we need to serve to you a cement with lower carbon cement, with the lower carbon footprint that can suit your application, and nevertheless a sort of a fine-tuning with your production. So it's more easiest way and can be handled here. While the second one is more on the engineers, so on the final, let me say, user, because you can save a square meter, but obviously there is a calculation based on the engineers, and so is the concept of design of the building. So it's more on the prescriptor, so we need to go up. In this case, this is more lobbying from the initial, let me say, value chain going down. This is something that it's our way, as Michele was mentioning before, to address the sustainability. On one side, let me say that is a scope 1, as mentioned by Michele, so it's more on our side, and then to deliver to you a competitive product. In the other way, it's more, let me say, a lobbying together with the customer and with you and to the prescriptor, to define a different way to, let me say, to design a concept of a new building. And then both sides, we have the cement, we have also our wine solution that, let me say, after the lunch will be shared with you. So now I leave the word to Soren that will deal more on the 2AL cement and the main application that, let me say, already guessed by some of your comments. And this is a key point that will start from 2024 with, let me say, a production with some sample from September 2023. This will be very important because together with Frank and so on, we also, let me say, once we are available the material, it's very important that the testing directly with the industrial partners, I would say, like you, it will be very important to give the feedback and to give also the sense of the potential of the cement, because it's not a cement, it's your product. This is the key point. We can do many testing on mortar in our lab, according to the standard, but the reality that cement should fit into your production process.
Let me start by introducing myself. My name is Søren Rasmussen. I have been employed here at Aalborg Portland and now Cementir since '92, being part of our company's transition from a small Danish company or big Danish company to be international company. And now we are in this transition, this journey towards net zero CO2. On the program it says that I'm going to speak about research, news and tools. But I have translated that into this presentation I'm going to give you. I'm named in our new Portland Limestone Cement based on the unique clinker that we produce here in Aalborg. Now you are here and you have seen our plant yesterday and seen the long wet kilns, which are unique. It's an old technology, but it enabled us to produce some very unique clinker that you will not find anywhere else in the world. And that gave us also the possibility to produce this new limestone cement from next year with what we hope is special cement properties because of these unique clinker. Yeah, my presentation is like divided into two, so I will start talking about our clinker here, and the second half will be about the new cement. As you learned yesterday, we have been producing cement here since 1889, but that was grey cement. It was since around 1930 that we started producing white cement, and at that time the plant looked like this. Today we are sitting over here somewhere. At that time we had the long rotary kilns. Not so long at that time, they was indoor in this building here, but today we have, yeah, that's better. Today we have extended the plant in this direction with all the kilns that you see today. And the first ones today that we have here is our white kilns. This is an old sign showing that already from the beginning of our white cement production, that cement was exported to a lot of different countries. And as Frank told us yesterday, we are representing by 12 countries in here, speaking 10 different languages. But I'm guessing that language is not represented here with Spanish, right? Nobody from Spain or from a Spanish-speaking country. But I'm not quite sure of the year for this sign, but at once white cement was branded like the Lion brand or the Lion cement. I had one of my Spanish-speaking colleagues to translate it, and what it says is that you can buy the Danish cement Lion brand El Legitimo. That means not it's legal to buy it, but it means that it's the real stuff, the real cement, it's the authentic Danish Lion brand that you can buy here. So already at that time, the cement was unique, at least on that sign, and sold somewhere in a Spanish-speaking country. Here at our plant today, as you know, we are producing the authentic Aalborg White cement, CEM 152.5R SR5 sulfate-resistant white cement, as we have been producing in that composition for at least 50 years, I guess. And also we know that we are now also supplying white cement from Egypt. We can supply you with the CEM 152.5 and also a CEM 2B cement. And coming up next year, we are proud to be able to supply you also a CEM 2A limestone cement, produced on the clinker that we have here in Aalborg. So my presentation today is regarding the cement based on the clinker from Aalborg and not the Egypt cement. So what is unique here, that is our raw materials, and they are wet, as we learned from Michael this morning. We have wet chalk, and therefore it was also a wet process, but that fits our production the best. We have wet kilns, meaning that we supply the raw material in a slurry, poured into this long tube of a kiln, and that's how we produce the white clinker. We can compare that to dry kiln process, and this is our grey production also here, which is a dry or semi-dry process. And those two processes are different and have different benefits and disadvantages. And we know, of course, a wet kiln process, the disadvantage is a very high energy needed compared to the grey, which are more energy efficient. And of course, that's a huge disadvantage. But we also have benefits from the wet kiln process. The raw feed is in a slurry. That means that we have all the raw materials, all the fine raw material particles is very intimate in suspension mixed together. So the feed into the kiln are more homogeneous than if we have powder raw meal fed into the kiln. In the wet kiln, we form very nice spherical nodules of uniform size, whereas in dry kiln, we have a much more dusty clinker coming out, meaning that the sizes of the clinker are from dust to maybe bigger balls. We have a long retention time in this kiln system. From entering to exit, it takes something like 6 hours for the material to go through, whereas in the dry kiln, it takes half an hour from start to exit. I'm tempted to say that we all know that slow cooking gives better food, and that's also the case maybe for our clinker, I hope. But one of the advantages of our wet kiln is the clinker that comes out are more pure. We have a lot of the volatiles which are in our raw material. That means the alkali, the sulfate, and the chloride is evaporated in the long kiln and goes out with the flue gas. So what is left in the clinker is a lower alkali content, a lower chloride content, a lower sulfate content. Whereas in the dry process, where we have a circulation and we have cyclones bringing back materials interaction with the flue gas, which are cold coming up. There we have a high concentration of those volatiles, and that also influences what is in the clinker. That's higher alkali, that's higher chloride, that's higher sulfate. So there's a benefit for the clinker, also because of these red raw materials, which already from the beginning forms the nodule, the small balls in the kiln. It's easier to form the nodules in the wet kiln than in the dry kiln, meaning that we can burn clinker with less iron content, with less aluminum content, which are the materials which forms the melt, which are there to form the nodules. So in a wet kiln, it's easier to melt, to form a clinker with a low C3A, with a low iron content. And we have no iron in white cement, no in white clinker. And in our special clinker, we have a low C3A. And that's only possible because of the wet kilns. So this is to show you an example of how it looks. Wet kiln, dry kiln, the clinker coming out here. You see, you should not compare the color, but you can compare the size. You can see here that these are small spherical clinker of not the same size, but at least a similar size. Whereas these clinker, which are from our Egypt plant, which are a dry plant, we see much more dust and also a bigger clinker nodules than over here. And that's a difference. This is only possible in a wet kiln. And that's bad, but we have learned, Michael told us this morning, that we have a heat recovery system at our plant, so we actually recover 25% of the energy put into the kiln. So even though we have these wet kilns, our total energy balance, you can say, is not that bad. And our EPD is not that bad for the cement. At first glance would look. And we produce gypsum, which are reused in our grey cement, recover the heat used for domestic heating, and also the dust from the white kiln with all those volatiles, it's high in alkali, high in sulfate, high in chloride, is also reused in our process.
So the gypsum, the byproduct of gypsum, does that provide all the gypsum for Aalborg production?
No, it's not enough. We use natural gypsum and we use desulfurization gypsum like this. And we also get gypsum from the power station nearby here.
How much of your gypsum would be from this by approximately?
I'm not sure about the number. 50%. So that's the clinker. And what are the key properties of these clinker? Because of our process, high whiteness, because of the uniformity in size, we can have more control of the heating, the temperature profile through the clinker, and also the cooling of the clinker is important that we capture the high temperature phases and quench very quickly. And also the oxidation that is happening on the clinker. The iron is locked in a state where it have no color. Very small amount of iron that are in there. If it is oxidized, it turns black, and we don't want that. So it's important with the size of the clinker. Give us high whiteness. We have a very low C3A content. That's possible because of the technique. So we have a sulfate-resistant cement. Of course, we have zero iron phase. Otherwise, we will not be white. We have a very high content of calcium silicate. That is the minerals that are giving the strength to the cement. Because we have no C4F, we have very little C3A. Only what is left is calcium silicate. So that's why we can have much higher silicates contents than in a normal grey clinker. Extremely low alkali content. When we say low alkali in Europe, you think about a cement that have 0.6 or less percent of alkalis. We have less than 0.2% of alkali. Extremely low chloride content is less than 0.01. Also, this is not because of the kiln technology, but we have zero chromate in this cement. That's because it's a raw material. So there's no need to chromium neutralize our white cement. It's born without any chromium. So that's unique. And if you look at the composition of our clinker, and see what does it do to the cement properties. Cement based on these clinker will have high strengths, especially the 28-day strengths will be high because of the very high content of calcium silicate and the low alkali. That give high strengths. The white cement on these clinker have more than 70 megapascal usually in 28-day strengths, and that's higher than almost every other cement. The low C3A, that allows us to have a sulfate-resistant cement. The low alkali content, that allows us to have a cement that never will have harmful alkali-silica reaction. You will not see it with the white cement. Also the low alkali, well, this is maybe a small thing, but when you have a cement which is sulfate-resistant with low C3A, you normally say, okay, but that cement is not good when you put it in seawater because it will not bind chloride because there is no aluminum to bind the chloride. But it's not the truth here because with low alkali, very low alkali content, that changed the balance between how much chloride is in the pore solution and how much is in the silicate phases. With a low alkali, more chloride is bound by the silicate phases. So actually this cement also have a good chloride binding capacity. Low C3A, low alkali, no C4F. That means that this clinker in cement gives us a cement which has a very good affinity or very good compatibility with the superplasticizing admixtures. You will see that when we try to compare concrete with our white cement with any other cement more or less, that you can always reduce the amount of superplasticizer needed in your concrete, very often to half the amount of superplasticizer. So instead of putting 5 or 6 or 7 kilograms per cubic meter of superplasticizer, you can go down to half and have the same fluidity, the same effect of the superplasticizer. And that effect we have tested in the laboratory. This graph showing water-cement ratio in a concrete, and here it shows the dosage of a superplasticizer. And this is different cement, and this violet color is the Aalborg White from Denmark. The others are also white cement. But you see, these concrete are different concrete, but with the same flow, with the same consistency. So all the points here are representing a concrete with the same flow spread. And if you have no superplasticizer, you need a lot of water, a high water cement ratio to have a concrete with a certain flow spread. Putting in superplasticizer, you can reduce the water and still have the same flow spread. I need to stand over here. Just to compare, if you look at, let's say we need a concrete with 0.45 in water cement ratio and a specific flow, then we should use around 0.4% of a superplasticizer with the cement from Aalborg. For all the other cement, we need a higher amount of superplasticizer to obtain the same flow with the same water cement ratio. So when we rank the cements, we can see cement number A, that's our cement, we need 0.38. Superplasticizer, and you can say that's a relative, that's 100%. But all the others, you need 150%, 160, 180, 190, and more than 2.5 times more superplasticizer to have the same flow. That is because of the unique clinker. This effect we will also transfer to our new limestone cement. And that brings me to the second half of the presentation. From next year, Aalborg White Limestone Cement CEM2 LL52.5R cement. We have designed this cement based on, what can I say, having two aims. One is, of course, to reduce our CO2 footprint. And the other one is to have a cement, you can say, benefiting from the quality of our clinker and giving us general purpose cement. And it will be at least 10% reduced compared to the cement we have today. Okay, and now I have shown you this maybe a little bit complicated figure. It's also taken from the Global Cement and Concrete Association, which we are a member. That is perspective of Global Cement and Concrete Association, how to achieve net zero carbon coming from concrete in 2050. And they put up 7 initiatives or actions that can be made in order to, or not can, but are needed in order to have net zero CO2 in 2050. It's about concrete, not only cement. But the biggest initiative that we need to do is, of course, the violet square here. 36% of the CO2 savings needs to come from carbon capture. So that's the biggest part, and that's going to happen at the cement producer side. But then the next biggest initiative, 22% of the reduction, needs to come from more efficient design and construction of our building and structures. So that's not the cement, that is actually how we produce the concrete and how we build our structures. Also, more efficient concrete production is a big issue. And then savings in clinker production, that means, for instance, shifting to biogas instead of fossil fuel. That could be helping us to reduce our CO2 footprint from clinker production. But then here, 9% of the CO2 savings needs to come from cement and binders. And that means that we need to produce cement with less clinker, which has a lower CO2 footprint. Not because of the clinker, but because of the substitution of the clinker. And that is what we are doing with the new limestone cement. That is that we are taking out 15% approximately of the clinker and replacing it by limestone. So why limestone? You could say that limestone, why is that the best option for us to put into our cement? Why it's not slag or something else? But we need, of course, a replacement material which have high whiteness. We need a replacement material which have a good influence on strength, especially on our early strength. We would like this cement to have a good early strength. And often when you put in a pozzolanic material, you reduce the early strength. We also need this material to have a good influence on rheology. When you put in calcined clay, sometimes calcined clay has a negative influence on rheology. So that are some of the considerations that we have made. And looking at different options of SCM materials, as supplementary cementitious materials that we could use, we could say limestone, slag, calcined clay, silica fume, or other, that could be fly ash. But there's obvious disadvantages by some of these. For instance, the fly ash is not white, it's dark. The slag and clay and silica fume, that could be obtained in a white quality, or at least semi-white quality. But limestone, the limestone we are going to use is ultra white. It's even more white than our clinker. Rheology aspect, limestone has a good influence on rheology. Slag also to some extent. Clay, no. The other, I have written a plus, it's okay. early strengths. Limestone has a good influence on early strengths. All the others, negative influence on early strengths. And then late strengths, limestone is not that good on late strengths, but as we saw, our clinker here has a very high late strength. It's okay for us to have a little bit of reduction of our 28-day strength. Supplementary material to contribute so much. So limestone for us is a good choice to put into the white cement. And also here at the plant, we have a quite advanced milling facility for the white cement production. We were talking about, Luke were asking about the particle size. Could it be better to grind these materials separately instead of co-grinding, blending? Now this is only limestone, it's not clay. But with our milling facility, which are shown here in a sketch, we actually have very good possibilities to co-grind the limestone and clinker. And without going into details, our milling facility is not just a ball mill. It consists of a roller press where everything goes through and being pre-crushed. Then it goes in two-chamber ball mill, but then the materials go through a separator. So we can control how much the largest particles are going separated and returned to the ball mill. We can decide the fraction how big should the particle be that are returned. And also in the separator, is driven by cold air. We are cooling the cement, so we are controlling the dewatering of the gypsum, how much semi-hydrate will be in the final cement. It's also part of a varying property of the cement. So with this setup, we are ready to make a limestone cement based on the white clinker. And by this process, we also see increased effect of the limestone compared to just adding those two, limestone and cement, separately. We have a good intimate mixing of the limestone particle and the clinker particle when we co-grind it instead of blending it. And then what is limestone? Now, not what is limestone, but many say that, okay, limestone is an inert filler. It doesn't do anything. It's like putting sand into your cement. It's not a pozzolanic material. And you're right, it's not a pozzolanic material in the classic sense, but it actually do contribute to the cement performance in a positive way. We see that limestone have actually 3 different effects on the cement performance. We are talking about a nucleation effect where the limestone is helping in the beginning to have cement reaction product formed. We're also talking about a chemical effect, that there are actually some reaction between limestone and cement minerals going together and forming new materials. So there is not a pozzolanic, but there is a chemical reaction which are helping, and there's a filler effect. So the nucleation effect is seen on this graph showing, we saw something similar yesterday in the laboratory where I was showing the calorimeter, that we were measuring how much energy is liberated within the first 24 hours after mixing with water. This is not our own doing, but it shows replace 50% of the cement with either limestone, quartz, fly ash. What happens to the reaction? The neat Portland cement, we have a heat or energy release starting at 4 hours, and then we have this the black curve release of energy showing the reaction of the cement. Putting in quartz or fly ash doesn't change very much, but putting in limestone, everything is moved to faster reaction. That's the nucleation effect of the limestone. That is also used by some of the admixture producers, new accelerators, where they use nanosilicate or nano calcium hydroxide particles to accelerate concrete. This is not nanoparticle, but at least it's fine small particles which act in the same way as nucleation sites for the chemical reaction. So this effect we will see in our cement. The chemical effect is another, that is that a small part of the calcium carbonate will dissolve and react with the aluminum phase in the cement, forming what is known as hemicarbonate or monocarbonate. This also a little complicated graph shows the amount of carbonate in the system and which minerals are formed. And this is a slow process, so this happens after weeks, but before 28 days. And you can say, okay, what happened is that those new reaction products actually increase the amount of volume which are formed. And if you have the same confined space, more volume means less porosity. So when this reaction happens, that is what I'm showing with dotted curve. The volume of the total volume of the system is higher, and that is why we have a positive influence on the strength. So with below around 2% of calcium carbonate, we have an optimum with the highest influence on strength, and then but all the way up to around 10% of carbonate, we can expect a positive influence on strength. And then the last one is maybe the most obvious, small particles being able to fit in between larger clinker particles give us a filler effect. So if dispersed, not a flocculated system, but in a dispersed system, this will densify also our cement paste and help increase again strength. And this we can see quite clearly, these 3 effects put together when we look at the 2-day strength of a limestone-filled cement. This graph shows from 0 to 20% of limestone, and then the 2-day strength relatively, so 100% being 0% of limestone. And what should be expected if there was no effect of the limestone should be, of course, a gradual decrease in strength corresponding to the amount of replacement, corresponding to the amount of limestone put in. But that is not what we see. We see that the strength is actually almost not influenced with the low amount of limestone, and there is up until around 10% before we really see a decrease in 2 days strength. So putting in limestone can give us the possibility to have high early strength with much less clinker. So even though we have not produced this cement full scale, we have done it in laboratory, we have also experience from our grey production. This is what we predict that the new cement will have properties. And if you look compared to the cement from Aalborg today and the two Egypt cements, 1 day strength, 22 megapascal, 23, 25. So we will have more or less the same 1 day strength as for the CEMII cements. And the fineness will not be much higher. And we also see that the setting time, it should be a little bit reduced because of the nucleation effect. What else? Water demand, we don't expect the water demand to go up. We actually expect it to be a little bit reduced. These numbers telling us the color of the cement, white, how green, how yellow. And because we use a very high quality limestone, actually we expect the color, maybe not the whiteness, but the tone of the green and yellow to be reduced a little bit. Again, based on what we have done in laboratory, but also based on our long-term experience with the limestone-filled cement in Denmark. We started back in '95 with the first limestone-filled cement. What we see is that semi-dry cast concrete products, this type of cement will be very good. We expect to have improved strength. We expect to have more stable, freshly cast product. You can put in more water maybe to the product without losing the form stability. This cement we expect to be good in precast, semi-dry cast products, as also you will see. What else? Wet cast concrete, precast concrete elements. Also here we expect this cement to have beneficial effect, mainly in self-compacting concrete. What we know from our present cement here is that the tendency to bleeding, the tendency to segregation when you make self-compacting concrete can be a challenge. But now when we have, let's say, 15% of limestone, finely ground limestone, we will have a more robust, less segregating, less bleeding concrete. And that will be good for concrete elements. Then I have mentioned bricklaying mortar, and that we also know that when we have the fine material in those type of products, workability and the consistency of these type of materials, grout mortar, bricklaying mortar, masonry mortar, is improved. So we also hope that this will be a segment for this cement. And then you saw yesterday also that there was a display of tile adhesive where we test different cement. We also think that this new cement will have an improved effect on workability for tile adhesives. But there is more workability. There's a lot of things that need to be fulfilled for tile adhesive. So what I are looking forward to is that coming autumn and next year, when you have the chance to test this cement to see what will be the results. Okay, so to sum it up, our new cement will benefit from our White Clinker here in Aalborg, those special properties that it has because of our process, and not the least because of our raw materials. And I have not talked about our raw materials, but that of course is also very important for the clinker. And based on, together with a high quality limestone, we hope this cement will be, I don't know, maybe the preferred one in the future rather than the same one. I don't know if that's good to say, but that could be a wish from my side. And we see this cement as an opportunity. It can be used for all applications. It will have maybe more benefits for some applications than others, but in general, this cement could be replaced, could be used in all applications. And that was the last one.